Thanks very much for coming along. I see a couple of familiar faces from 2 weeks ago, so those of you who saw me bluffing my way through energy economics will now have a chance to see an energy economist talking about energy economics. Dr. Giorgio Castagneto-Gissey is a teaching fellow here in economics and business. I'm delighted he's coming on today to talk to us about the economic analysis, econometric analysis that he's been doing on electricity pricing in EU markets. Giorgio, over to you.
Thank you very much. So, thank you very much all of you for attending to this summer. I would like to thank myself, the organizers, for giving me the chance to present my research here at the UCL Institute for Sustainable Resources. So I'm Dr. Giorgio Castagneto-Gissey. I am a teaching fellow currently at UCL, where I teach subjects such as econometrics, macroeconomics, finance, and a few more. I have a master's degree in economics from the Warwick Economics Department, and I also have a PhD from Imperial College London. In fact, I'm here today to present to you my 3 research papers that I've published during my time at Imperial College during my PhD. In fact, the title of my PhD thesis was Electricity and Energy Price Interactions in Modern EU Markets, which is also the title of today's presentation. So, just a brief overview on the structure of today's presentation. I will start with a few with the general aims and the motivations that brought me to write this thesis. I will then present to you each of my 3 research papers. So the first study relates to the combination of exchange rates and oil prices and their impacts on the volatility of electricity prices in the European Union. The second study relates to electricity market competition in Europe, whereas the last third and final study relates to electricity market integration in the EU. So the common denominator for all these papers is the econometric analysis of electricity prices of the European Union. So I will finally summarize the main findings, and this is followed by some concluding remarks. So just a few words on the background relating to the thesis. Until not very long ago, until the 1990s, the electricity sectors around the world used to be state-owned or at least very heavily regulated, until the worldwide liberalization movement, which through a process of deregulation brought about an introduction, an increased level of competition across electricity markets. The main aim was in fact that of eliminating the national monopolies from the generation, transmission and distribution sectors. So therefore, given this important transition in electricity markets around the world, prices have gone from reflecting mainly government policies and costs to reflecting essentially market fundamentals. So econometric research on electricity prices has not really started flourishing until the early 2010s, and therefore it can still be considered a quite new and relatively unexplored field of research. So this this PhD thesis, aims at providing novel insights on the determinants of electricity prices in the European Union, as well as the interactions between electricity and energy prices in Europe during the period from the end of the noughties boom and the early 2010s. So throughout the thesis, throughout the 3 main research papers, which came from the 3 substantive chapters of the thesis, I ask questions such as: how did electricity and energy prices interact throughout this period? How did the volatility of electricity prices respond to the 2008 financial crisis across European markets? And how competitive are European electricity markets? And finally, how are electricity markets in the EU integrating over time? So this is my first research paper. It was published in 2014 on the Journal of Energy Markets, and here I mainly ask what is the effect on electricity price volatility of changes in the volatility of oil prices and exchange rates against the US dollar, because in fact oil prices are denominated in US dollars. So here I find that the transmission, there's a large transmission of volatility from exchange rates and oil prices on electricity spot prices, and that this volatility improved very much after the 2008 financial crisis. And in addition, the innovations coming from oil prices and exchange rates, their effect on electricity price volatility have become more symmetric after the financial crisis. The second paper, published on always in 2014 on energy policy, asks how competitive are European electricity markets. So we look at how electricity generators integrate the cost of carbon emissions into their electricity prices. So it's a question of how competitive European electricity markets are. As a summary, I find that electricity producers in the EU tended to, in phase 2 of the ETS, tended to integrate the cost of carbon emission allowances much more than they should have. The third paper, published always in 2014 on energy economics, is a paper in which I, together with other two co-authors from the neuroscience department in France, we apply a very interesting technique which is used to understand how the brain works. We apply that to energy economics for the first time in order to understand how electricity markets are integrating over time. So we ask how are EU markets integrating in the period from 2007 to 2012, and we find that there is a large peak in the integration of European electricity markets around the end of 2011, and this could perhaps have been explained by the introduction of the implementation of the third energy package. So let's start by order with the first of the three papers. This paper is entitled Oil Prices, Exchange Rates and Electricity Spot Prices and Paper Insights from EU Markets. Again, it was published on the Journal of Energy Markets in 2014 and co-authored by Professor Richard Green of Imperial College London. It was also presented at the last, at the 2012 Austin conference by the IAE. So a brief introduction on this topic. Electricity is priced in national currencies, however it's produced using fuels such as oil, for example, which are priced in US dollars. We therefore might expect that electricity prices are a function of the domestic currency to the US dollar exchange rate and of the oil price. So therefore we test this hypothesis for a sample of European markets before and after the subprime crisis contagion on European markets. So what questions do we ask? The first question we ask is, do oil prices and exchange rates against the US dollar in terms of returns and volatility affect wholesale electricity spot prices in terms of return and volatility? The second question is there a difference between these effects before and after the subprime crisis contagion on European markets? And finally, does electricity price volatility respond symmetrically to both positive and negative shocks coming from oil prices and exchange rates? So the literature background related to this topic mainly relates to two research papers by Munoz and Dickey in 2009 and Sadorsky in 2000. The first of these papers finds through the application of co-integration methods that the volatility, but not the levels of Spanish electricity prices, were affected by the euro-dollar exchange rate, while Sadorsky, also using co-integration procedures as well as applying a Granger-causality analysis, finds the first piece of evidence in favor of a transmission of exogenous exchange rate shocks to energy prices. So what data do we use to carry out this analysis? We use our endogenous data relates to wholesale electricity spot market prices in terms of weekday daily reference price data relating to the countries of France, Germany, Italy, the Netherlands, Spain, and the United Kingdom. and the electricity price data is of course in euros or pound sterling per megawatt hour. So here is the fuel mix of the different countries that we have chosen, and we have chosen 3 European countries, namely France, Spain and Germany, which use greater amounts of nuclear, hydro and alternative resources to produce electricity, as being less sensitive to changes in crude oil prices as well as to the euro-dollar exchange rate. And we compared these with 3 EU27 countries, or the Netherlands, Italy and the UK, which are instead more dependent on fossil fuels. So our exogenous data obviously relates to oil prices and exchange rates from the EIA and Thomson Reuters respectively. So this is how oil prices behaved from 2005 to 2011 throughout our study period. So we can see that there was a very large peak in oil prices, and that was coinciding with the outbreak of the financial crisis. And then oil prices very much dropped after that period. So we can also see that the US dollar is the least valuable currency and the pound sterling is the most valuable one. So what empirical models do we use to carry out this analysis? We specify a normal model for the conditional mean of electricity price returns, as well as we assume a GARCH process, GARCH model for the volatility of electricity price return, which is also known as the conditional variance. So we use maximum likelihood estimator in order to estimate our parameters. The conditional mean is a normal process, an autoregressive moving average process. Actually, it's only an autoregressive process in our case. So a normal 1-0 specification, which provides a parsimonious description of a weakly stationary stochastic process in terms of the autoregressive component. As in order to describe the conditional variance or the conditional volatility of electricity price returns, we use a GARCH process, which is basically a normal specification which is assumed for the error variance. So you can see this over here. However, because the GARCH 1.1 assumes a symmetric innovation response of the autoregressive volatility, we'd rather use a nonlinear GARCH. However, we are able to introduce a function G1, which is able to remove GARCH 1.1 non-stationarity, and therefore we use an N-GARCH extension by Higgins and Vera, which is able to provide a symmetric, an asymmetric response, which is what we are looking for, and in fact a stationary behavior for our conditional variance of electricity price returns. So we also model exogenous spillover effects, so we embed an exponential functional form within the conditional variance equation in order to model these exogenous spillover effects coming from the oil price and the euro-dollar exchange rate in order to define the multiplicative heteroscedasticity component. So we expect oil prices to have a positive effect on the returns and the volatility of electricity prices, and the same about the exchange rate. In terms of the combination of the two, we expect an additional effect. So here are our results. So we have results relating to the GARCH model and the N-GARCH model. However, I'll only show you the N-GARCH model results because of time constraints. However, I can tell you then that the N-GARCH model was much more performing compared to the GARCH model. So in many cases, so I will show you the results of the N-GARCH model for the period before the financial crisis and after the financial crisis in terms of the conditional mean results and the conditional variance results. So starting with the conditional mean, in many cases, the level of returns in either the oil price or the exchange rate had very little impact on the level of electricity price returns, both in the first period and in the period after the financial crisis. However, the volatility of these prices affected the volatility of electricity prices in most of our studied countries. However, the volatility of exchange rates and oil prices had an effect on the electricity price volatility in each of the countries studied after the financial crisis, and in addition, these electricity price return volatilities were asymmetrically affected in the period after the financial crisis by our exogenous variables. So what can be said in terms of the GARCH and AR-GARCH models? So we can say that the AR-GARCH model was superior in terms of performance compared to the GARCH model, and this represented this showed that the leverage effect was very well represented across our entire sample of countries. In addition, we find that the exchange rate and the oil price had a very large symmetric effect after the financial crisis, and in general there was an incredibly large transmission of volatility from exchange rates and oil prices on the volatility of electricity prices in the period after the financial crisis. What does it mean when I say that that asymmetry has decreased? Asymmetry coming from the effects of oil prices and exchange rate has decreased by as much as 54% after the financial crisis, implying that oil price and exchange rate volatility induced a more balanced effect on electricity prices only after the financial crisis contagion on European markets. So what is the main contribution of this paper? That has shown that the financial crisis has brought a more stabilized, a more balanced effect of oil prices and exchange rates on electricity prices after the financial crisis, as well as that there is a very large transmission of volatility from our exogenous variables onto electricity price volatility, but only after the financial crisis. So what can we say in terms of the policy implications? We have discussed volatility of electricity prices, so therefore this volatility, or basically risk, has many implications for the way in which low carbon generators should be supported. In fact, what we wouldn't want is a volatile wholesale price that will be passed to electricity consumers, because this implies very large risks to the consumer's bills. This is also very unattractive to the majority of low carbon generators, whose costs are not linked to those of fossil fuel prices. So what is the main policy implication is that if we ensure that payments to these generators are largely delinked from the overall level of power prices, such as, for example, with feed-in tariffs or the UK government's proposed electricity market reform, in this way we'll be able to reduce the risk for generators and consumers alike. So now forget everything I've said, and unless you have some questions, you can write them down or you can ask them now. I now start talking about the second paper, so let's not get confused. So, do you have a question?
I had a small question. Besides the exchange rates and oil price, what were the other variables that were plugged into?
There were only the exchange rates against the dollar and the oil price. We were interested exactly in that relationship because basically the oil price is denominated in terms of US dollars, and so we wanted to check that in combination to the euro dollar or the pound sterling against the dollar exchange rate. So let's start with the second paper. The second paper is a single authored paper, was published in 2014 on the journal Energy Policy, and it's entitled Electricity and Carbon Forward Price Interactions, an Assessment of ETS Phase 2. So this paper was presented at the latest international conference by the IAEA in New York. And the main questions of this paper relate to understanding how competitive electricity markets are. So we ask, how much do European electricity generators integrate the cost of their carbon emission allowances into their electricity prices? This is also a question of competitiveness, so we are asking how competitive are European electricity markets. In addition, we also ask a further question. So the question is, what are the main drivers of electricity prices during phase 2 of the European Union emission trading system? So what is missing from previous work that has been done on this topic? So the topic is how much do electricity generators integrate the cost of their carbon emission allowances into their electricity prices? So this is also called the pass-through effect. So the carbon cost pass-through effect. How much carbon prices are passed through to consumers. So there's quite a lot of literature on this topic, very much indeed. However, all the past papers just go and estimate empirical models in order to understand what is the change in electricity price from a unit increase in the carbon price. However, what is missing from these models is the fact that we are not taking into account the carbon intensity of the different generation units as well as the thermal efficiency. So none of these takes that into account, and that is exactly the motivation of this paper. We would like to understand how carbon prices are integrated into electricity prices, considering, of course, the carbon intensity of the different generation units, which will provide a more ad hoc derivation of the pass-through effect in relation to the different countries. So what data do we use to carry out this analysis? We use daily year ahead prices, so daily 1 year forward contract prices. So we aim at explaining the electricity prices of France, Germany, Nord Pool, which includes Norway, Sweden, Finland, and Denmark, and the UK. So we explain electricity 1 year forward prices by using as explanatory variables coal prices and gas prices, and of course carbon prices relating to the entirety of the period relating to the second phase of the European Green Emission Trading System. We also employ stock market indices because we know that forward prices are affected by expectations of future economic activity in contrast with the spot prices, which instead mainly depend, for example, on temperatures. So we use forward prices because we want to eliminate the daily variability that is instead inherent into electricity prices. So this is how electricity year ahead prices related to Germany, France, the UK, and Nord Pool, how they behaved from 2008, the start of 2008 to the end of 2012. So they behave quite similarly to coal and gas 1 year forward prices, and of course to the carbon price in terms of the 1 year forward carbon price. So you can see that the behavior is quite similar to the electricity forward prices. And finally, the stock market indices of the different countries, which are used as a proxy for forecasts of future economic activity on which electricity forward prices depend on. So after having stationarized our data, we input them in the model. However, we use a combination of 3 different models. So we use this in order to derive the pass-through rates of the carbon cost into electricity prices. So we start with by using a VAR model in order to detect the significant interactions between all of our variables. We then use linear pairwise Granger-causality in order to identify the causal relationships between our variables. We're mainly interested in checking whether there's causality running from the carbon price to the electricity price, which until now is known as the pass-through effect. However, I'm slightly skeptical about this fact because it is very important to also not only understand what is the change in the electricity price from a unit change in the carbon price, but also it is important to consider the carbon intensity of the inherent generation methods. So we would estimate the change in the electricity price from a unit rise in the carbon price from the GARCH models, or the asymmetric GARCH models, the one that best fits our data. However, once we've done that, this is our main innovation, that we scale the change in the electricity price from a unit rise in the carbon price by what I call effective carbon intensity. So therefore, I adjust the GARCH model rate by considering thermal efficiency and carbon intensity. So here is the bar model, which we just simply use to derive the significant interactions between our variables. This is the Granger-causality, a very standard technique which we use to derive, understand which variables are causing which, with an eye on the relationship between carbon prices and electricity prices. And finally, the GARCH models. So the GARCH model, as we've seen before, for the GARCH model we have a conditional mean equation and a conditional variance equation. The conditional mean equation, that's where we derive our coefficient of variation with all the exogenous variables, including the carbon price, within our exogenous matrix. And of course, electricity prices are an autoregressive process. So we also estimate, of course, the conditional variance equation. However, that does not directly impact on our estimation of the coefficient of variation of the carbon price and electricity prices. So the most important part, once we have derived that the change in the electricity price from a unit rise in the carbon price, we call that omega carbon. And so how do we find the pass-through effect? We just take that number, which tells us a unit, the change in the electricity price from a unit change in the carbon price, and we divide it by TCC, which is the theoretical carbon cost. And this is given by 0.9, or the carbon intensity of coal-fired generation, times the lambda C, so the average plant share, the average coal plant share at the margin, and we add that up with the this term, so 0.35. So therefore, the carbon intensity of gas-fired generation, and we multiply that by the average gas plant share of the margin. How do we find the average gas and coal plant shares at the margin? We simply find them by multiplying the thermal efficiency of coal or gas times omega coal or omega gas, which are basically the derivative of the electricity price with respect to coal or gas. So basically the GARCH model, conditional mean model coefficient. So in this way we are able to find a more realistic pass-through rate, which takes into account both carbon intensity of the generation units as well as thermal efficiency. So we don't really have much time to go through the results of the bar model, Granger-causality, and the GARCH models. However, we just use these numbers here, which are the effect of the carbon price on the electricity price, and we scale those factors after considering thermal efficiency and carbon intensity. In this way, we are able to find the implied coal share of the margin and the implied gas share of the margin. Most importantly, we're able to find the carbon cost pass-through rate, so the effect of the carbon price on the electricity price. So we find significant pass-through rates for Germany, the UK, and Nord Pool, whereas for France we were not able to detect a significant causal relationship directly from the carbon price to the electricity price. So we do not consider that. However, for Germany, the UK, and Nord Pool, we find very large carbon cost pass-through rates, especially for Germany and Nord Pool, which show that electricity generators during phase 2 of the ETS, on average, integrated the cost of carbon emissions by about 35 and 37% more compared to the competitive threshold, which should be 100%. Similarly, the UK is about 9% over the competitive threshold. So therefore, electricity generators integrated too much the cost of carbon emission into their electricity prices. So what can we say about electricity markets? Are they competitive? Did they look like they were competitive during phase 2 of the ETS? It doesn't look like, because they integrated the cost of carbon emissions much more than they should have, and so they made profit. And this is in line with the notion of windfall profits, which has occurred during the phase 2 of the ETS. What can we say instead about the determinant of electricity forward prices, which is more important, coal or gas? The coal or gas price, we found that coal was more influential in determining electricity prices compared to gas, and this was probably a result of the falling carbon prices during the study period. The carbon market crashed twice, and also probably because of the low gas prices, because of the shale gas bonanza in the United States, which also contributed by decreasing coal prices. So therefore, coal prices have become coal has become a very profitable production unit. And we can see this also by analyzing the marginal profitability of coal over gas-fired generation. The marginal profitability of coal over gas-fired generation is nothing but the difference between the clean dark spread and the clean spark spread. And so every time the series is above 0, it means that coal is marginally more profitable than gas. And so we can actually see that on average, for each of our four markets, coal was actually more profitable than gas, and from midway through, so about 2010 until the end of 2012, there also seems to be a quite linear trend increasing the marginal profitability of coal over gas. And so this shows the prominence of coal during phase 2 of the ETS, and if this situation were to be sustained in the long term, so that carbon, coal and gas prices were to be so low, then coal would continue to be exploited as it was during phase 2 of the ETS, and this would represent a problem for the achievement of emission reduction objectives by the EU as a whole, and of course of the single member states, considering the EU burden sharing agreement. In addition, this paper finds a novel and very simple method to assess pass-through rates of carbon costs into electricity prices. So we are able to augment previous models by considering very importantly carbon intensity and thermal efficiency. So in fact, past studies have actually tended to underestimate the pass-through rates of carbon prices into electricity prices. However, by considering carbon intensity and thermal efficiency, we are able to find higher pass-through rates, which underline how uncompetitive electricity markets have been during phase 2 of the UTS. So this is it for the second paper. If you have any questions, please do ask them.
Did you find any bidirectionality between coal prices and electricity prices?
Between coal prices and electricity prices?
Yes.
Well, I can't really remember that because there were a bunch of different, hundreds of different relationships. But I really cannot remember this. I'm sorry, because I worked on this about a year ago, and it was not really a central aspect of the research. So I'm afraid I cannot give you an answer for that. So if you don't have any more questions, however, if you're interested, you can still email me, and I can tell you because it's definitely in my thesis. So finally, the third and final study is entitled Dynamic Complex Networks of Electricity Spot Prices, a Novel Approach to Market Integration. So this paper was published always in 2014 on the journal Energy Economics and was co-authored by Dr. David Falani and Dr. Childs of La Sorbonne University of Paris. So they came from a neuroscientific department, and we worked together to apply a technique that was very well known in the neurosciences, and we applied this technique, which is used to model how the brain works, how different parts of the brain connect with each other, and we used that in order to assess electricity market integration. So this paper was presented at the latest European conference by the IAE in Düsseldorf in 2013. The main research aims of this paper are, so that the main aim is actually that of understanding how electricity markets are integrated over time. So by doing so, we introduce graph theory in energy economics and in econometric studies for the first time. So just a little background on the topic. First, there are three main directives by the European Commission. The first one in 1996 was mainly about transparency of energy markets. The second directive of 2002 instead was mainly about the European member states establishing independent national regulatory authorities for energy markets. And finally, the third and most important directive is the one of 2009, which provided a mandatory separation of independent system operators and promoted the interconnection between the different EU member states. Most importantly, in relation to our topic, the third directive introduced novel frameworks that would improve the integration of electricity and energy markets. So what is the previous work, what is the main literature background relating to this paper? So the topic is how well integrated are European electricity markets. So there is quite a lot of literature published on this topic, and all these papers present a lot of contrasting results. So for example, Zachman, 2008, through principal component analysis, found that the market integration hypothesis for electricity markets in Europe could be accepted in some cases, but not in other cases. So there was not a definitive answer. It was a definitive answer, but there is a large contrast between different kinds of markets. Robinson, 2007, using a B convergence and co-integration test, found instead that yes, electricity markets in Europe are indeed integrating, while instead Barcelona, 2004, used a correlation and co-integration analysis only to find that no, electricity markets in Europe are not integrating. Banach and Freda instead, 2010, found that interconnector capacity was able to explain market integration in Europe. And similarly, Calantzis and Milonas, 2010, found that not only interconnection capacity can explain whether electricity markets are integrated, but also proximity of their countries under analysis. So what is the main novelty of this study? So until now, authors have only considered pairs of electricity prices in order to check whether they are integrating or not. Instead, we use a large sample of electricity prices to understand whether the whole system seems to be integrating. So this is the main novelty of our study. So in order to do so, we use 13 electricity spot prices relating to the countries of Belgium, the Netherlands, the UK, Denmark, Finland, Norway, and Sweden from Nord Pool, France, Germany, Switzerland, Italy, Portugal, and Spain. So we use intraday or hourly spot prices from Thomson Reuters, and the period of interest is between 2007 and 2012. So our main methodology represents our main innovation main contribution for academic literature, and this technique is known as network theory, and in fact the electricity markets can also be seen as an evolving network. Therefore, the complex pattern of propagation between the different countries' electricity spot prices gives rise to what can be effectively considered an interconnected system or a dynamic network of electricity prices. So we therefore applied modern network theory to our sample of 13 electricity spot prices, and network theory is basically a mathematical framework, a data-intensive mathematical framework which is capable to characterize connected systems with a great deal of efficacy. So how do theoretical networks work? So they are formed by nodes or vertices and edges or arcs. So in our case, the nodes are the electricity prices in a certain point in time, or period, but a certain point in time, whereas the edges or the arcs are demonstrate the relationship between the electricity prices. So for example, if we have an electricity price A and electricity price B, if there is an arrow direction from A to B, that means that this arrow must have a weight, which is given by the degree of linear pairwise Granger-causality. So therefore, by Granger-causality, we are giving a weight to the relationship between an electricity price A and an electricity price B. In fact, our time-varying network was obtained indeed by using Granger-causality. We computed Granger-causality through an M-bar model, through a multivariate autoregressive model of order 4 over a temporal window of 720 days, 720 points, or 30 days. In this way, we refer to a sliding window with a shift of 4 points, or in other words, we estimated a network every 4 hours, resulting in a total of 7,651 shifts. So we estimated a network every 4 hours, and the difference between the shifts is in fact 4 hours, which serves to us to understand about the interactions, the Granger-causal interactions between the prices. So what are the main integration factors that we use? We use global and local integration factors. The global connection density shows the level of interactivity of our sample of electricity prices over time, and this depends on the connectivity in degree of the different markets. In fact, the node connectivity in degree is simply the sum of the incoming Granger-causal degrees incoming to a certain node in a certain period of time. So if we sum those up for a certain country, we get the sum of the incoming Granger-causal degrees, and these are reflected in terms of the entire sample of the electricity price in the global connection density series, which shows the interactivity of a sample of electricity prices over time. And there is also the node connectivity at degree, which instead shows the number of outgoing causal interactions from a certain node in a certain period of time. So this is a simple way for you to understand how our model works. So say that we have, for example, a network, instead of 13 electricity prices, we have a network of 5 electricity prices. So if you take, for example, node number 3, which can be on a certain electricity price number 3, we can see that this is Granger caused by electricity price number 5 and electricity price number 1 by factors of 0.91 and 0.72 respectively. So we can see this from what we call the adjacency matrix, which shows these interactions in terms of our matrix. And so for node number 3, we can see that node 1 is causing node number 3, and number 5 is also causing node number 3. So of course the same electricity price Granger causality is 0. So we are assuming that causality from nodes 2 and 4 is 0 because it's not significant, for example. In fact, we don't see any there. So if we sum our incoming causality, so 0.72 and 0.91, we get the in degree. So the total number of incoming causalities in a certain shift. On the other hand, we have the horizontal entries of the matrix are instead the outgoing causality. So it's just the other way around. So the sum of our entries in the vertical, in the columns of the matrix will tell us how much incoming causality a certain node has in a certain period of time. And this is the connectivity in degree, which will be reflected inside the global connection density series together with the in degrees from other electricity prices. So our results. These are the instruments or the in degree strengths of our that we were able to derive from our model. So on the y-axis we have each unit of the y-axis is simply a different market. So we have Belgium, Denmark, Finland, France, and so on until the UK. And each of these shifts, each of these, on the x-axis instead, we have the 7,651 shifts, or 4 hours each. So from the 11th of August 2007 up to the 30th of June 2012. And so the more incoming causality into a certain node, into a certain electricity price, the darker the color. So we can see that there is quite a lot of interaction going on towards the end of 2011. In addition, studying the electricity price in degrees, we were able to find something interesting that that might explain, probably not fully, that electricity prices of neighboring countries are more related. In fact, the electricity spot price in degree behavior of Belgium and the Netherlands is more closely tied compared to those of Nord Pool countries, which are Sweden, Denmark, Finland, and Norway, which behave more similarly between each other. So, in addition, in order to understand whether this technique is reliable for understanding how electricity markets integrate over time, we carry out t-tests on our in degree electricity price in degree data, as well as correlation tests. The t-tests, which I'm showing right here, are used to check whether the electricity price mean in degrees of coupled markets have increased after the coupling date or the interconnector commissioning date. So we take all the possible events of market coupling or interconnector commissioning throughout our study period, and we study those. We study the in degrees of those countries which have coupled or have gone through interconnection. So we can see that the mean in degree of these electricity prices has increased in all 100% of our cases after the coupling date or the interconnector commissioning date. Mm-hmm. And so therefore there is a positive change, a very large positive change for the mean in degrees of electricity prices after the coupling date, implying that we were able from this data to understand that there has been a structural change in the electricity markets. In addition, we use correlation tests in order to check whether couples of electricity prices which have been subject to either market coupling or interconnector commissioning have increased in terms of the correlation between electricity price in degrees after the coupling date or the interconnector commissioning date. So you can see that the correlation between pairs of electricity prices after market coupling or interconnector commissioning has increased greatly, just besides this outlier, has increased greatly for basically 99.9% of our cases. So we can see that in relation to the Nord cable that connected Norway and the Netherlands, and the BritNet cable which connected the UK and the Netherlands. And the same thing for all our other possible events of interconnector commissioning or market coupling. So finally, what can we say about the overall level of integration of our electricity markets? This is the global connection density series, so you can see everything that is either above or below our confidence bounds is significant. So in this case, we have 4 different peaks, but mainly there is an incredibly large peak at the end of 2011, and we also applied the regime switching model on this series, which is able to tell us that on the 24th of October 2011 there was a jump in the series, and this established itself into another regime. So we actually went to see when there has been the effective implementation by the European Commission of the third energy package, and maybe by chance, maybe not, this has occurred just 4 days before our date in which we recorded the jump in the global connection density series. So here is an example of our network representation to show you what's going on behind the model. So this is an example of the network, the graph, and the relative adjacency matrix in relation to our the point in which we have the highest peak. So around this time, we recorded the relative adjacency matrix, and it looks something like this. So you can see there were quite a lot of connections between our countries, quite a lot of interactions, Granger-causality interactions. So we instead, just for comparison, go to look at the graph of the network in a period of time representing the average global connection density, and we can see that there is very little connection, which is reflected in the relative adjacency matrix. So again, global connectivity remained around 2.11%. The percentage is the measurement unit for the global connection density series. And the density stayed around a mean level of 2.11% across the period 2008 to 2011, and we have seen the 4 significant peaks at around 3 to 4%. However, the main peak, which reached about 7%, occurred between the 5th of October and the 16th of December 2011, and this resulted in an increase compared to the preceding mean level of about 2.4 times. So what can we say about the global connectivity indicator and the local connectivity indicator? So this is the very first time this technique was applied to energy economics, so you might want to study the topic a little bit more, but the first impressions are quite good. So that the global connectivity indicator showed a very large peak in the integration of European markets, and our technique picked this up, and maybe by chance, maybe not, this coincided with a 4-day delay to the implementation by the European Commission of the third energy package. In relation to the local connectivity indicators, we have seen through t-tests and correlation tests that our data, our in-degree electricity price and degree data was able to reflect important structural changes that occurred between our electricity markets. So we propose network theory as a suitable tool to assess electricity markets both from the a global or European-wide level and from a local perspective, so between to assess the integration between couples of electricity markets and from a global perspective. However, what can be said in terms of the general level of integration of European markets throughout our study period, there were both positive and negative changes over the upper bound and below the lower bound throughout our period, and these cancelled out, therefore providing some evidence in favor, some evidence to say that the electricity market integration is proceeding at a very slow rate. So just a few general conclusion about my three papers. So the first paper found that the 2008 financial crisis has contributed by decreasing the asymmetry of the response of European electricity price volatility to shocks in both oil prices and exchange rate volatility, and we found that there was a very large transmission of volatility from both exchange rates and oil prices onto electricity prices in terms of volatility only after the subprime crisis. And we said that this is very unattractive to most low carbon generators whose costs are not linked to those fossil fuel price of fossil fuels. So the second paper instead found that electricity markets are not very competitive by augmenting past models by including thermal efficiency and carbon intensity of the different generation units, and we found an excessive pass-through rate for Germany, the UK, and Nord Pool. We also find that coal prices have a larger effect on electricity prices compared to gas prices, and this derives probably from the increased profitability of European electricity generators in using coal with respect to gas, probably as a result of low gas and low carbon prices. Finally, the third paper that we have just discussed applies a new technique coming from the neurosciences for the first time to energy economics, and that finds that this technique was able to detect fundamental changes in the integration of European electricity markets, both at the local level and at the global level. So therefore, by finding that there was the introduction of the third energy package, which coincided to our largest jump in the global connection density series, as well as our local connectivity data over the price in degrees, which found that it is possible to understand when electricity market structure changes drastically, either through the introduction of interconnection or market coupling more simply. So therefore, we believe that dynamic complex networks can be a suitable tool in order to understand the dynamic behavior as well as the interactions of European electricity prices, both from a national perspective and an overall European-wide perspective in relation to the topic of electricity market integration. So as a final word, I would like to thank to acknowledge financial support from the UK Economic and Social Research Council, as well as I would like to thank very much Professor Richard Green of Imperial College London, who was my supervisor during my PhD studies and has offered very useful comments and suggestions on the paper. So I'd like to thank you as well very much for coming here today to listen to this talk about my research.
Thanks very much.
Giorgio. I see you've cannily timed it so that we finished at almost exactly 1:30, which like it's just as you finished. So we might have time for a couple of clarification questions, but then we'll all have to go eat. I hope it'll be gratifying to economists, engineers and policymakers alike that 4 days after measures were introduced to integrate EU electricity markets, you saw closer synchronisation of EU electricity prices, and that increased physical coupling of national grids leads to increased coupling of prices on those networks. I mean, good news for all of us in that the market's actually doing things we hoped it might do with those interventions. Do we have any clarification questions? They will have to be quick because we're already pressed for time now. It was so crystal clear that you probably know that. In that case, I'll take that one, and then we will finish at 1:30.
When you say interconnector commissioning, does that also imply market couplings, or because I don't understand what
that's different. So we have considered the events of market coupling and the events of interconnector commissioning. So interconnector commissioning is simply when an interconnector unites the electricity markets of different countries. So, for example, the Nord cable or the GridNet cable. So GridNet cable was between the UK and the Netherlands. Whereas market coupling is more general, just implies that new regulations which have integrated two electricity market systems have been put in place.
Great. In that case, we're done. Thank you very much all for coming along, and I hope you'll join us again in 2 weeks for our next speaker. But if you'll join me once more in thanking Giorgio again.